Okay, so for the in-class lab, from next week, we'll be working on Wednesday, Thursday, Friday. Monday and Tuesday will be lecture. Okay.
Zoom.
Anyone get any question?
Could you repeat, please? Could you repeat, teacher? Excuse me.
What?
He wants you to repeat what you said. He said, repeat what you said.
Oh, what I said from next week in class lab will be on Wednesday, Thursday, and Friday. And the lecture will be on Monday and Tuesday.
On Zoom.
Yeah, in the Zoom.
Okay, thank you.
You're welcome.
Hey, Professor, is that just for next week, or is that going to be for the rest of the semester?
That's supposed to be to the rest of the semester. When we get more students get into the lab, then we can start from Tuesday, adding one more day. Okay, so now let me get into my iPad. Okay, I try to go over quickly, go through the diode. That's what we already done last week. Before we can move to the next one. Okay, you guys already working in the lab and you're already working with the generator. The thing I want to bring it up today, we're talking about voltage divider law. That we'll be using a lot. Okay, if you're looking into the circuitry, you get R1, R2. And basically you can get the current flow here. Hi. If you want to calculate the V out, basically V out equal I times R joke. Okay? So normally you can calculate the I, then you can using that formula. So you already know I will be A divide total resistance. Okay? Then you can apply VL equal I times R joke. However, they can get another way, make it shorter. Voltage divider law. You want the voltage here. So you can calculate V out equal A times R joule. That's what we call voltage divider law. You don't have to calculate the current. Okay? And now, okay, so you can get same thing. Okay, if I want to calculate the V out, what V out equal?
It's the current times R3 divided by R1 plus R2 plus R3.
Okay, basically normally you calculate the V out mean from here to the route. So they can be I times R joule plus R3 divide total R1 R2 R3. Then you can calculate V out. You can calculate the I already. Okay. I equal A divide
Hey, Mr. Pham, can I ask a question?
Just a minute. Okay,
Yeah, that's what my question was going to be, because the I times the R2, R3 is voltage.
right.
So I didn't, yeah, you fixed it. Go ahead, never mind.
Okay. Now that is normally you do calculation. However, I want to using the voltage divider. Then V out equal what? Voltage divider.
It's the voltage times R2 plus R3 divided by R total.
Perfect. A time R2 R3 divide total. That is what we call voltage divider law. That will be applied for the theory. This is circuitry, okay? So any question on voltage divider law? That means if you want to calculate the voltage from a certain point to the route, then you can using voltage divider, can say the time. Instead, you have to calculate the current. Then you can calculate the voltage. Okay?
Okay.
Yeah, now. You already, I'm talking about students working on AC1 circuit. That means you're working with a generator. Okay? This is a generator. Okay? That's what we're talking about, generator. And that's what normally they call IF. And that is the output. That's what we're talking about, our load or VR. Okay, now do you know the output of a generator? They get a resistance. That's what right here. Normally, how many ohms?
Real small, maybe like 10 ohms,
Come on.
5 or 10.
Who knows?
RL.
Now I'm talking about internal resistance
Oh, like 470 or something?
of the generator. I want to know normally how many ohm resistance. Hey, you guys working and you guys not pay attention.
50.
Who knows what the output resistance of the generator?
50 ohms.
Now you offer.
Exactly.
50.
50 ohm.
50.
If you're looking into the generator, at the output, you can see 50 ohm. That means the output of the generator, 50 ohm. And now they connect to the load. Okay. And basically, they want to know what the value for RF. What that mean? That means when they connect RL here, they can adjust RL. That means you can vary resistance on RL. Okay. Now they're telling you set that to be 10 volt, peak to peak, 1 kilohertz. Okay. So when they try to adjust the voltage until Vout equal 5 volt. That's telling you what?
It's telling you that RL and RS are equal.
Exactly. They're telling you RL, RS equal. So if you measure RL 50 ohm, that means RS 50 ohm. However, I work with a few students. They cannot get that part. The thing is they enter 30 ohm, 35 ohm. That's not correct. Even it's a very, very simple. Okay? I can tell you the problem. Maybe this is not quite not quite 50 ohm.
In other words, you're saying it's plus or minus 50 based on some tolerance.
No, that's really our tolerance. So that's why when they measure only 30 ohm, they enter incorrect. Then I can telling you, maybe output of the generator not 50 ohm. So what can we do now?
You adjust the RL to meet the whatever resistance of the generator is?
No, you adjust RL until Vout equal 5 volt, a half of 10 volt.
Yeah, but you said the generator RS is not.
Right. RS equal RL. Then after you adjust 5 volt, then now you measure the RL, you get only 30 ohm. You enter 30 ohm, they draw. I can tell you the answer will be 50 ohm, not 30. If you enter whatever you measure, you cannot get correction.
So how do you count for the fact that RS is not what it's supposed to be?
That's what I try to telling you. Okay? So, in order to get this pocket correct, I can tell you enter 50 ohm. The thing is, their software set it to 50 ohm. Now, I try to tell you, how do we prove RS is not 50? Okay, what you can do. First thing, you adjust RL. Okay, to 50 ohm. How can we do?
Measure the output from RS and generator and see what the drop should be.
No. Right now I say, first thing I want you to adjust RL to 50 ohm using DMM. Okay? DMM will be go to high and low. Okay? So this is resistor here. However, that's not connect to the generator. Okay? The thing is when you connect to the generator, you cannot measure resistance. Okay? So you just measure across the IL and adjust it until you get 50 ohm. So you know for sure you get this is 50. And now you connect to the circuitry. Okay, you adjust until you get 5 volt ahead. Whatever value of the IL will be the same with the IS. The reason the IS inside the generator is not correct. Why? The thing is in the path, when you connect the output generator to somewhere else, damage that output. So that resistance burn out. And they have to remove that resistor, change another one. Maybe they not change for correct one. Okay? So on the first part of the AC1, when you have to measure the resistance this way, I can tell you the value to get it part will be 50 ohm. Not a big deal. Otherwise, you have to get another circuit board.
Also, Mr. Pam, you're saying on some of the lab boat AC1s, this particular circuit block on some of them may not be working correctly.
1 and 2.
Okay.
The thing is, ANSO 50 ohm. What happened? They believe RS have to be 50 ohm, but they not. They already burn out and regen another resistor. Maybe the value is not really correct. That's why.
Is that because of DCs being hooked up into the circuit and frying the generator?
Exactly. For some reason, they connect to the high voltage, 12 volt or 10 volt. They cook that resistor output of the generator. So we have to open generator. I think Mr. Lu already did it for me.
A couple of times. Well, that's why I was questioning your initial question of how to measure whether or not 50 ohms was part of that circuit, because it's the safety, that 50 ohms is actually the safety resistance of the generator.
Yeah.
So if you're putting in that additional resistor, that's kind of doing a subtraction on the original 50 coming out. So if it's a drop, then that 50, that what you just showed right there, that 50 ohms is measuring actually the 50 ohms in the generator, right? Or the generator's not hooked up.
You cannot measure directly from the output of generator.
So there would be a plus R1, or excuse me, measuring the internal generator plus that additional resistor. So you would have 50 ohms.
Yeah, that's what you are able to do.
All right.
Mr. Pham, my only question was, once you adjusted RL for the 50 ohms, how do you know what RS is inside the generator? Because you said it was faulty or it got burned out. So if you didn't know the exact value of the replacement one, how would you go about finding out what the new value of RS is that you replaced?
Okay, now, when you get a RL for 50 ohm, if RS equals 50 ohm, you adjust the output to be 5 volt.
Right.
Okay. Then they suppose RS have to be 50. If RS not 50, and you have to adjust more than 5 volt or less than 5 volt. That is not correct.
What about the technique to hook up channel 1 to a ground and measure the signal while the channel is hooked up to ground? Can't you determine whether or not the resistor is fried internally doing a calibration check?
That means you say you connect the DMM low side to the ground, high side to the output generator, right?
Well, on some of those, they have a internal calibration where you can take a channel 1 and hook it up to the ground post on the equipment and then do the internal software calibration, and it'll
yeah, that you're talking about calibration. Okay.
But that's also monitoring. Correct me if I'm wrong. Isn't that verifying that 50 ohms?
Yeah. Okay. Here we go. Now the diode, we already, one more time. Diode basically a rectification device. Rectification means converting AC to DC. The voltage from anode to the cathode, that's what we call a VD. Okay. voltage of the diode. VD all the time, VA, VC. And now, any voltage VD greater than I'm talking about ideal. What VD equal?
0.
Perfect. 0. So if VD greater than 0, diode on mean conducting. Also on means forward bias. And if VD less than 0, diode will be off. Off means reverse bias, or non-conducting.
No, no current flow.
Right. C. Open circuit. No current can be flowing. Okay. However, that's just talking about VD equals 0. Normally, you're not working with ideal diode. You're working with the second approximation. VD 0.7 volt for manual, for silicon, sorry. Silicon diode. And VD 0.3 manual. Okay. Same thing. VD greater than 0.7. Diode on. LED diode on. Okay. So that is also telling you what happened if they connect, okay, or they revert bias. And this, what happened is telling you they can be on and they can be off, like the switch. They can open or close. Okay. And when you're working with the diode, remember, when you say the diode on, you cannot see any diode anymore. In this one, I know the diode will be on. So when they on, you must be substitute the diode by the battery. Plus, minus 0.7 volt. Okay? So in this circuitry, they say what V out. V out means from output to the ground. So when you measure the voltage across the battery, you get battery voltage. So that's why diode on or off, then I say diode on V out equal 0.7 volt. If you calculate the current I mean the current flow here. That means the difference between V out minus V bias divide R. Okay? And after you can get current I, you can calculate the VR. I time R. That's
And
a
Mr.
yeah.
And Mr. Pham, shouldn't that be the bias voltage minus V out over R? Because then that would make it positive.
Which one? What number? 1, 2, 3, 4.
Number 3.
Number 3, they want the current I.
Yeah, so isn't it 10 volts minus 0.7?
Yeah. Current I.
So then the V out and the bias should be switched around in that formula, shouldn't it?
Yeah, the thing is V bias will be bigger.
I know, but I'm saying where you wrote, shouldn't that be
They're
switched
supposed to be. Correct.
They're supposed to be switched around.
Right. They're supposed to be V bias.
Minus V out. Yeah, like that.
Correct.
I had a quick question, Mr. Pham.
Go ahead.
I know that you've said before that a silicone diode is much more common than a germanium.
Exactly.
Is there a specific application where you would see germanium, or are those sort of being phased out? Is that something that was used before more often and now it's switched to silicone?
Now, normally, most of the circuitry they're using the silicon. However, in the different type of the circuitry they're using germanium, when they want that voltage to turn on, not too high.
Okay.
So depending on design, depending on the application. Okay, so this one we already done it. Okay, I don't want to go over. Now, the next one, I want to make sure you must understand. Otherwise, you cannot get through it. We're talking about Zener diode. Okay. With the Zener diode, when you go to buy Zener diode, you must be telling the people what voltage Zener you want. 5 volt, 10 volt, 20 volt, 15 volt. Otherwise, they cannot sell it. Okay? The Zener diode try to protect the circuitry at a certain voltage they want. This is a symbol, okay, for the Zener. And now, Zener, they can be break down. They can be working like normal diode. So first thing, when they break it down, then the Zener must be changed to this voltage. Positive here, negative here. Okay? V here will be the Zener voltage. If they not break down, they're just working like normal, then this diode here must be substituted by this battery. Negative on this side, positive on this side. The thing is, you want to solve the problem with the diode or Zener diode, remember, must be substitute Zener symbol to the battery. Okay? Okay, now, for this circuitry here, the Zener voltage will be 10 volts. And the voltage here will be 20 volts. So the question is it a Zener breakdown or not breakdown? How do we know? If for the Zener, if you don't know they breakdown or not breakdown, you cannot do anything. So my question for this circuitry here, tell me, how do I know this Zener will be breakdown or not breakdown or working normal, whatever?
I think it would break down.
You figured out what V out is without the diode, then if it's the V out is greater than 10 volts, then it breaks down.
That is very, very good. Okay. If you say breakdown, no. How do you know they break it down? You have to prove the voltage here have to be higher than 10. So in order to do, before you can say breakdown or not, you suppose no diode here. What V out? If you don't have any diode here, what V out?
20 volts.
20. And 20 higher than 10.
Yes.
So they break down. But you cannot say they break down. You have to prove. Another proof, again, make sure no Zener there. What V out? Okay, so in this case, Zener breakdown. V out equal 10 volts. If you get questions, stop me, okay? The thing is that are very, very basic before we can adding just a minute, okay? Okay, go ahead. Get a question? Hello? You guys hear me?
Yeah, letter B.
Yes.
Okay, any question?
We're on letter B now.
Now, I can 20 volt, okay, to 5 volt. Question is, what V out if V in 5 volt?
Hey, Mr. Pham, didn't you skip letter B?
What do you mean letter B?
You're doing the example, so you skip letter B.
No.
Oh.
I suppose you guys already know.
Oh, okay, I'm sorry.
Yeah, the thing is, I just emphasize on the basic thing you must be know.
Okay, that's okay.
Okay, now, if I turn the input to 5 volt, question A, what we out?
It acts like a regular diode.
Except it would be negative 0.7.
What if we out?
5 volts.
5 volt, perfect. If V in equal 5 volt, and you suppose to get 5 volt here, correct? And Zener not break down. So look like Zener open. So that look like they open here.
Right.
So that's why VL equal 5 volt.
Because the Zener is a voltage limiter, so V out can never be higher than the Zener voltage, right?
Yeah, cannot be higher than Zener.
So if V in is higher than Zener, V out equals VZ. If V in is lower than the Zener voltage, then V out equals V in.
Whatever. but the thing is, this is a simple circuitry. You can get a more adding thing to the circuitry we cannot say. However, what I'm telling you, if they break down, then V equal VZ. V break down. If they not break down and they not working normal, then they open. Okay? And the last thing I want to tell again. So if you can answer the question, that means you understand. We're asking for understanding. Okay, now I can get into minus 20 volt. Okay. If VA what V out? Telling me.
Minus 0.7.
What V out equal?
Minus 20 volts.
Vn equals 20. Okay.
What V out equal? Okay, now you get minus 20 here. Right?
Right.
You get 0 volt here. correct?
Right. The diode is not in breakdown at all because it's not in breakdown.
Working like normal.
Yeah.
So they normal working. You substitute positive, negative.
So it's minus 0.7 or something?
Exactly. Okay. So I can say diode working normal.
The anode is more positive than the cathode.
Yeah.
So that makes it forward bias.
Exactly. Okay. That the three things can be happen to the Xeno. Then when you see it, you know how to do what to do. Question. No, go. I don't want to do it. We already did.
These one here, these one can be tricky, Mr. Pham.
Now, for this circuitry, for the circuitry here, you apply sideways. The peak to peak 10 volt. Okay, so you connect the Xeno with the 3 volt breakdown. So for the input, positive here. So basically they are 5 volt and the Xeno will be break it down to only 3 volt right here. You see that? Higher than 3, they break it down. And when they get a negative cycle, that means you get a minus 5 volt here. This is a 0. Okay? Then now Xeno working like normal. That's what we just saw it. They will be equal minus 0.7. You understand the first circuitry, then you understand the second. No big deal. So that will be telling you if the voltage higher than the Xeno, they cut it off to the Xeno voltage. Otherwise, Xeno can be not break down, or they can be working like normal diode. Make sure if you get questions, bring it up, okay? Otherwise, we don't have a chance to going back anymore. You have to keep moving. This one, same thing, okay? Positive, then one will be breakdown. The other one will be normal. So that's why positive VG1 breakdown, adding to 0.7. And for the negative cycle, okay, G2 breakdown, they will be minus VG1 minus 0.7. Same thing in here. You can look into that, okay? Same thing. Light emitting diode. That's a LED. We're working on the digital circuitry. You can see LED, turn it on, they can red, okay, or green, whatever. and that 7 segment, A, B, C, D, E, F, G, 7. Inside each segment, you just get a diode. And you can turn on or turn off each diode to make a number or the letter. Okay. And now you can get the rectify. They just given you the picture for the rectify. What that means? Converting AC to DC. You get AC on this side, go to the rectify. They coming up with DC, post DC. And this will be telling you halfway rectify. Why halfway? The thing is, full wave will be from here, going down, going up. That up and down, that's a full wave. However, the rectify only positive, not negative. So that's why they call halfway rectify. They rectify only positive, or they can rectify only negative. Okay. And also now you can see, you get AC right here. Go to rectify. Okay. Basically, you can get like we just talking in here. Okay. Just the halfway rectify. And then go to the filter. And now you can get the output will be a VDC. However, VDC on the top, they still get sideways. That's what they call a ripple, the noise. Okay. And they try to clear on off this noise here, just get the DC only. So they can use the regulator. Just a picture for you to see. Okay. Now, we start with the halfway. Easy. Halfway means rectify only positive. You see that? And negative here, 0. Okay? This is a halfway. When they rectify both sides, positive, negative, and negative, they will be a full wave rectify. However, when they draw in here, they telling you one thing. That means they want VD equal 0. However, if VD not equal 0, see how they look like. Okay. If VD equal 0.7 volt. So when you get the positive, diode will be on, right? And I said on, they must be substituted by battery. And the value will be 0.7 volt. So at the output here, you can get 2 signals. One will be DC, and another one will be AC. So when I draw it, I can draw for you right here. Minus 0.7 volt DC. If you're looking on the scope, you can see you can get minus 0.7 volt. Okay. And This will be V peak here. They will be go from here. Okay. So what the V peak supposed to be? If I say you get a 5 volt here, V peak 5 volt, then this will be 5 volt. Okay. So if you're looking on this circuitry, what V peak equal?
4.3.
4.3 volt. Okay. The thing is V peak will be measured from 0. Okay. And now they already going down 0.7. So that's why you get only 4.3. Okay. When they draw in here, that means they draw for ideal. That means VD equals 0. Okay. Make sure you understand one, and the next one will be more easy. Okay, by the way, in here they already telling you for the halfway rectifier, frequency input, okay, and the output the same. If you get a 1 kilohertz, then the output also 1 kilohertz. Okay, and for the second approximation, you want V peak out, you have to take V peak in minus 0.7 for silicon diode. Okay, next one, transformer. Basically, transformer will be transform one voltage to the other. VP here they call a primary voltage. VS will be secondary voltage. And NP, that means how many turns of the wire on the primary. Okay, and NS, how many turns for the secondary voltage. So you can calculate the secondary voltage using this formula. NS times V primary divide NP. Okay, and also they can give it to you. If NS higher than NP, okay, you get a step-up transformer. Step-up transformer, that means you get 120 volt in primary. However, when you go secondary, you get 240. It's step up. Or they can be stepped down. If you get 120 volt here and you get 24 volt here, that's a step down, depending on NS and NP, the wiring. Okay. Now, for this circuitry here, we call halfway rectifier. They using the transformer 2 to 1. Okay. The first secondary voltage, they want to calculate the VP here. That's easy, right? VP here equal V primary, okay, times V NS1 divide and peak. So that means the voltage here will be at 156 divided by 2. And also they say they want to know the peak output voltage. Okay, so what the output voltage here? So this is the halfway. So you get the sideways positive, turn on the zener, turn on the diode. So the output will be DC minus 0.7. And positive will be, we already know, 156 divided by 2. You have to divide to minus 0.7. Okay? That is a rectified output. If the frequency 1K, what frequency out? We already know. That same frequency 1K.
Hey, Mr. Pham, I hate to, because I know you don't want to go over stuff too much, but just only on this one, the peak secondary voltage, this would be like 78 volts, correct?
156 divided by 2.
Yeah, on the secondary side. And then the output would be minus 0.7.
Okay, now V out peak, right? Will be equal. Now, I have to say this one for correct. This is the V peak right here. V secondary. Okay.
And that's 78.
Right. Okay. V at P equal 156 times 1. 2. What you get?
That should be 78, shouldn't it? Anybody else out there got that?
78.
Yeah.
Yep.
Okay. And now this is the V out.
Now you subtract 0.7.
Exactly. V out peak will be equal 7 at V peak minus 0.7. Seven 7.3. Okay.
All right.
Frequency.
Frequency.
Equal FE.
So it's the same.
Yeah. Okay. Okay.
All right.
Make sure if you get a question, okay? But go ahead. Otherwise, you will be working on the lab. If you understand that, easy for you. Now, we get what we call a full wave rectifier. Now you can see easy to recognize. This is your input here, positive, negative. So positive, they rectify. Negative, they rectify. So that's why they call a full wave rectifier. Okay? Then, in this case, they're using the transformer. However, they get a round right here. So that's what they call a center tap transformer, CT. Okay, now, what for center tap transformer? That means when you get a primary voltage, they go into the second one here. They divide that voltage, okay, one from here to here. The secondary. However, they divide from here to here and from here to here. Divide a half. So the value for this first one will be V secondary divided by 2. Okay? And the second one, the same thing. I given you example. If you get a 50 volt, and now they're supposed to be the same on the secondary, then this one will be 25. This one will be 25. Only thing is, at this side, you can see the signal look like. On the other side, same thing, they opposite. Okay, that's the point. This positive and this will be negative. Okay, so now you can see when you get the positive here, this signal will be on. Okay, that's why you get this on. Okay, then when you get a negative here, this is positive here, turn this on. So this negative here also be on. So that's why they could keep going. That's what they call full wave rectifier. Finally, when you're looking into output here, you must be telling this is the output of the full wave rectifier.
So whatever voltage you get is minus 1.4 because each diode is 0.7.
Exactly. We'll see. Okay. Now, they already telling you here, DC average, we who care, I don't care DC average. However, we really care frequency output will be double frequency input. If you get a 1 kilohertz coming in, output will be 2 kilohertz. Okay. For the practical diode, VD equals 0.7. V peak out equals V peak in minus 0.7. That I already given to you in order to calculate the V peak at the output. Okay, this is just a more detail for full wave rectifier. Okay, we already telling you. This is primary. This is a V secondary from here to here. And the value for this sideway, V secondary divide 2. Same thing. Only thing is, this positive, this will be negative. This negative, this positive. Okay? So that's why you get a full wave. And now they've given you more detail here. For the positive, then that's why this guy on you get that one, okay? And for the negative, this guy on, you get another one, okay? So this a little more detail for you. Output will be VP primary divided by 2 minus 0.7. Okay, just more. Okay, you can look into that FullWaveRectifier. That's just given you the picture, okay? This is your input and this output. They rectify positive, they rectify negative. That's why they get FullWave. Okay, I think that is the last for that part here. Same way, FullWaveRectifier. However, they're using the diode with normal transformer. They call a bridge rectifier. They're working exactly center tap transformer. But the thing is, the cost for the center tap cost too much. They just using for a diode. They can do the same. So that's why most of the power supply circuitry, you can see the bridge rectifier, just a FullWaveRectifier, but cheaper. Okay, so basically for the positive here, okay, that means you get a positive right here. Then you have to know which diode will be on and which diode will be off. I just gave it to you. 10 volt. Peak to peak. Okay, so I can say D1, D2, D3, D4. So if we add, okay, can be any voltage positive. Example, 5 volt, for example. So which diode on, which diode off. So if we add equal quantity, then this side we add will be negative. So when they on positive here, I know D2 will be on. Okay, what else?
D4.
Normally you can get 2 on, 2 off. So
D4.
for sure, I get positive. I know D2 on.
2 and 4.
Exactly. D4 also off. How come they off? I'm telling you. This side, we said negative, right? This is ground. Ground is 0 volt, higher than negative. So that's why D4 off. So the first taps here, D2. D4 on. Okay, D1, D3 will be off. Okay, now, when you get into negative cycle, Vf now will be negative. Then, on this side, okay, Vf positive. They have to be opposite.
And Mr. Fram, you're referring to where the nodes come together from the transformer and meet the diodes, correct?
Right.
Correct.
Okay. When you get negative here, with diode on,
And Mr. Fram, can you use your pointer?
1 and 3.
1 and 3.
okay, you get a round right here. 0 volt. Okay.
Mr. Fram, use your pointer.
What?
Yeah, like that. Yeah, your pointer.
Okay. 0 volt here. And now I say negative here. D1 on. Right? Okay. Then also, this side positive, then D3 on. Okay. So basically, for the negative cycle, negative part right here, D1 will be on, D3 will be on, okay? And the other will be off. That's what normally they will be asking you. For positive input, which diode will be on, or which diode will be off. Okay, so that's why you still get the full wave rectifier. Okay, basically they prefer using the bridge rectifier. This is just a more detail for you guys to read, okay? For the bridge rectifier, you try to spend time to read it, okay? And if they want to calculate the V pitch out, and that they give it to you here, okay? V pitch out minus 1.4. The thing is, 2 diode on equal 0.7. That's why 1.4. Okay. Capacitor input, that's just for information. Okay. So that's why you can get the ripple signal. Charging or discharging. If you want to more designer, you can go into detail. Okay, that's it. Any question?
Mr. Fram, can you go?
Yeah.
I missed the first part of the class. Can you go back to what document needs to be referred to? Your document referral page.
You can download it from website.
Yeah.
Or you can watch the videos.
Yeah, it will be loaded.
You usually have that the display screen, the first display screen before you start class, the one that shows the download.
Normally, you understand you have to, if you're coming early, then I'm still sharing what you need to download. Normally, after 5:15, then I have to go to give a lecture. The reason I didn't go is not exactly 5. The thing is lecture and some students have to work it, so they cannot be exactly 5 o'clock. So that's why a little late, let me 5. No big deal. Okay, what I recommend, we need to really understand, okay? You guys can get a certificate, okay, different way. Like you do a left vote, you already get the answer from someone else. You keep enter the answer. And you can get it correct. But you don't know anything. That's why after you say, I done for AC1 circuitry board, before you go to the AC2, and you will get a 1 left volt test for both AC1. That means the circuitry will be using the same, but will be a different value, different frequency. If you don't know, you not quite understand, you cannot get through it.
Mr. Pham, a quick question.
Yeah, go ahead.
With the bridge rectifier, is the output frequency also twice the input frequency with the center tap?
You mean
full wave?
Yeah, the full wave, yeah.
So it would be twice the frequency as the inputs for the output.
Right, the relation. That means the output will be double.
Okay, thank you.
You are welcome. And you understand, FullWaveRectifier, they can using the center tap transformer, or they using the bridge rectifier. They work in same thing.
Mr. Pham, so basically on the half-wave rectifier, the input and output frequency is the same.
Exactly.
And then on the full wave and the bridge rectifier, it's double?
Output double.
On the full wave and the bridge?
Right.
Okay, full wave and bridge. Okay.
They both full wave.
I think it's because the definition of a cycle is when a signal repeats. So full cycle for a full wave rectification would be each hump because it repeats with each hump. But because it's a full wave, it does both the positive and negative. You get twice the number of humps as you would from positive and negative for a repeating signal.
Yeah, that means positive they rectify, negative they rectify also. That's why they call a full wave. Otherwise, they rectify only positive or negative. They just a halfway.
And if I'm correct, in electronics, the bridge circuit and with the 4 diodes and the one with the 2 diodes, they're both considered full wave.
Exactly.
Okay, all right.
Only different is they using normal transformer, or they using center tap transformer.
Okay, got you. Thank you.
Yeah, the thing is, next meeting we will be talking about transistor. Make sure you download that handout. Okay, the thing is I try to get as much at the lecture. Basically, you must get through, and I can help you to solving on the left phone. That means when you doing on the left phone, what you supposed to do. If you not get output correct, what can we do? That's what I want to teach. Okay, I still keep fighting with my camera. Camera working with one computer, but it's not on the other one. So I still get a lot of work, try to make it working. Okay, and I try to do like, we can using it at YouTube, so you can watch it, no big deal. You don't have to be in the meeting. Very soon, your guys will be doing more lab than lecture. That means right now you get 3 days, but very soon you can get 4 days in class lab. Okay, and finally 5 days try to get the lab done.
But that depends on how many total students you have, right?
Exactly. Depending on how many students able to get into the lab. I don't think at this time, I still get a lot of problems. I don't care. CT1, whatever. I cannot do anything. Before the COVID-19, I controlled the class, everything. Now, during this time, CT control everything. They don't know what the program doing.
The city is big brother.
Like, whatever they want me to do, that I do it. I don't care. If I think, okay, I cannot do it, then I quit. Okay. So, otherwise, we'll see you guys next week.
All right. Thank you, Mr. Pham. Thank you. Have a good weekend.
All right, now.
Thank you.
Have a good night.
Good night.
Good night.
Thank you. Mr. Pham?
Yeah.
Thank you. Good night.
Good night.
Yeah, Mr. Pham, this is Silviano. I was wondering, can you put up the video for September 20th back up?
Trendy.
Because I was, I hadn't finished taking some notes from that lecture.
That means on what day is it?
September 20th.
20. Okay, that means third week. That's a second week.
Yeah.
Third week.
Yeah, and you could still keep September 24th and the 27th up.
Yeah, that's still there.
Okay, if you keep it there. Okay, thank you, Mr. Pham. Have a good weekend.
Hey, Mr. Pham, you keep all those videos up, right?
Right, for this semester.
Okay, so if whatever's up from the beginning all the way to the end will stay up, correct?
Right.
Okay, good.
Okay.
Thank you.
Good
Have
night.
a good weekend. Good night.
Yeah.